Understanding chirality and RNS configurations. Chirality means a molecule is not superimposable on its mirror image. For example, if you were to take your hands and lay them on top of each other, no matter how many times you twist or turn your hands, it can never look identical. So that means it's not superimposable and are chiral. But if you were to take two spoons, they can obviously look identical. So that means that those spoons are superimposable and are achiral. Now, we will go better explaining that in enantiomers, but for now, just remember that. And a chiral carbon is a carbon attached to 4 different groups. So if we look at this carbon right here, we can see that it has a chlorine group, fluorine, bromine, and hydrogen group. So that's 4 different groups, and therefore this carbon is chiral. Now, when assigning R and S, well, first you want to find the R and S configuration of this chiral carbon, right? And R configuration is clockwise, and an S is anticlockwise. And to find out if this molecule is clockwise or anticlockwise, there goes to a priority list where the highest priority is going to be the highest atomic number, and the lowest priority is going to be the lowest atomic number. So if we look at our periodic table here, we can see that bromine is the highest priority because it's the highest atomic number, and then chlorine, and then fluorine, and obviously hydrogen is last. So let's label it. We got our first, second, third, and fourth. Now when assigning the direction, you want to go from first to second to third, just ignoring that fourth. So when you do that, it's going to be clockwise and therefore BR. But the funny thing about chirality is that when assigning it, you want the lowest priority group, which is hydrogen in this example, to be on the dash, which is not on the dash, it's on the solid line. So since it's not on the dash, you just want to flip it. So instead of that direction, it's going to be anti-clockwise, and it's going to be an S, right? And you could just remember to just inverse the configuration when the hydrogen is not, or the lowest priority is not on the dash, or you can conceptualize this as just the carbon here, the chlorine here, and if you were to rotate this molecule, right, the dash means it's behind it. So if you were to imagine rotating it, it would look, it would look like this. Now, if we were to do a priority of this, it would be in that S, right? Because it's just rotating it. You're not actually swapping anything. You just want to rotate the molecule to where the lowest priority is on the dash. So, and that's an S. But in this example, it's asking for a mirror plane. So if we were to take the mirror plane on this, it would actually be an enantiomer. Enantiomers are a pair of molecules that are mirror images of each other but cannot be superimposed. So if we were to draw this molecule across the mirror plane, so it will be an enantiomer, it would look like this. Our carbon in the middle with our chlorine on the top. And since this molecule is flipped, the hydrogen would be over here, and the bromine would be over here, and the fluorine would be over here. And if we were to assign priority on this, it'd be 1, 2, 3. And since it's flipped, it's going to go like this, and that's going to be an R. And you notice that when enantiomers, the S and R are going to be opposite, right? Because this one's an S, so since it's an enantiomer, this one has to be an R. Now, if we look at more examples here, we can see that these are not chiral carbons because they both have multiple of the same group, and we need 4 different groups, so those are not chiral. And when assigning priority, we can see that there's a carbon bond over here, and with 3 hydrogens. There's a carbon bond on this one with 1 carbon bond and 2 hydrogen bonds. There's a carbon bond on this one with 2 carbon bonds and 1 hydrogen bond. And obviously there's a hydrogen right here and a wedge. So we gotta take that into account as this is the 4th priority. And you just wanna go through. So hydrogen, carbon, carbon. This is gonna be a 3rd because it's the lowest atomic number. Now, hydrogen, carbon. Okay, this is going to be second. This is going to be first, right? Because it has another carbon on top. So we can tell that it's going to go in this direction, but since the hydrogen is on the wedge, we're going to flip it, and it's going to go like this, and it's going to be an S. And now that we understand that, I'm going to quickly go through this for the sake of time. So it's going to be 1, 2, 3, and it's going to go like this. It's going to be an S, and the hydrogen's already on the dash, so no need to flip. And it's going to be 1, 2, 3, but hydrogen's on the wedge, so we're going to flip it. It's going to be an S. Whoops, that's in clockwise, so it's going to be an R. And 1, 2, 3, hydrogen's on dash, no need to flip it. So that's going to be R again. And 1, 2, 3, that's going to be on the S. 1, 2, 3, that's going to be on the R. Now, if we were to look at these closer, A and B, right, they have 2 S's and 2 R's, so therefore these are enantiomers. Now, if we were to look at B and C, these are going to be diastereomers. And what are diastereomers? Diastereomers are stereoisomers that are not mirror image of each other's, but, since they're stereoisomers, they have the same connectivity and such. So, as you can see that this one has R, and this one has an S and R. So these are diastereomers. Do dia, and also A and C are also diastereomers, right? Because it's the same thing, SNS and SNR. Now, constitutional isomers are same molecular formula but different atom connectivity. So D would be constitutional isomers of A, B, and C, right? Because they all have the same molecular formula, but this one has different connectivity, so it would be constitutional isomers. And meso compounds are molecules that have 2 or more chiral centers, but are overall achiral because of an internal plane of symmetry. Now, if we look at this molecule right here, there's an internal plane of symmetry already drawn for us. It has that 2 chiral centers, but it doesn't have the opposite R and S. So that means this one is chiral. But if you look at this one with internal plane of symmetry again, this one has the opposite R and S, so it's a meso compound. And if we look at this one with the internal plane of symmetry, it has that 2 chiral centers and that symmetry, as I said, and opposite R and S, so it's a meso compound. And if we were to look at this one, well, does it have that internal plane of symmetry? Well, no, it doesn't. Because if you were to draw this as a chair conformation, which you can draw for cyclohexanes, it would be the wedge, the bond going up, and the dash means the bond going down. And these bonds are actually in opposite directions, so there is no internal plane of symmetry. So this is therefore chiral. Now, this is a spectral example because it's a cyclohexane, but it's still something that can trick you, so do not be tricked by this.